Okay, welcome back to this first session of shorter talks. The schedule is very dense, so you should try to stick to 25 minutes, and that includes questions. We're already running 5 minutes late, but Felix still will have 25 minutes for his talk, including questions. He will talk about the three-level variant of parareal, and he has an analysis of this three-level method. So I'm looking forward to your talk, Felix.
Thank you very much, Martin, for the introduction, and thank you and to Florence for inviting me here to this very nice center in Marseille. It's the first time I'm here, and it's one of the first conferences that I'm attending after, after the pandemic started. It's really nice to see all of you again in 3D. It's really wonderful. So I'm going to talk about analysis of three-level variants of parareal, and you're going to see that this work, well, this is still sort of in progress, so I don't have all the answers yet, but I have some analysis. And this all started with some discussions that I had in one of the last two conferences that I attended before the pandemic started. I'm going to point out where things are going to happen. So I'm going to introduce a variant of three-level parareal that I'm analyzing, and I'm going to show you how I go about doing it, and I show you a couple of examples, for PDEs. Okay, so most of you know how parareal works, so just think of this as fixing notation. Okay, so I have a fine grid. This is an interval in time. I'm trying to integrate from the left to the right with fine time steps. Many fine time steps, and then what I'm going to do is, I split this up into subintervals. Okay, I'm setting this up for parareal, and then my F operator essentially integrates over one subintervals over many of these fine time steps. Okay, so that's my fine propagator, and then I have a coarse propagator, which I denote by G for grossier. Okay. And it goes over the same subinterval, but this is supposed to be a coarser approximation, so maybe either lower order or you take larger time steps. But F and G here goes over the same interval. It takes you from one point to the next in time, at the same place. Okay? It's a two-level method. That's why I have the fine propagator and the coarse propagator. Okay? And then these approximations that are at these time points are denoted by UN, and N is the index for the time points, okay? And then I'm running an iterative method, so the iteration count is the K that's in the superscript, okay? So here the idea is to say that if I know the solution exactly at these coarse time points, then I can just fill in the solution in between, by integrating over these subintervals, and then now the work is completely in parallel. So the whole game here is to find out what the solution of the fine problem is on these coarse time points. Okay, so that's the idea. And then the way parareal works is it has a recurrence formula. So basically I have to have an initial guess at all these time points, these coarse time points. So what I do is I just take the coarse propagator and then I just propagate sequentially over the whole interval just to get some initial guess on these time points. And this coarse propagator is supposed to be cheap so that even if I run it sequentially, it's supposed to finish very quickly. So the bulk of the work is in the fine integration. Okay, so I populate these sequentially just to get initial values, and then once I have the initial guess, then I run in parallel on each of these subintervals the fine integration over many fine time steps, high order, very expensive. But now this is all done in parallel at the same time using my initial guess, okay? And then once I finish the fine integration, you're not going to get the exact solution right away. There's going to be some mismatch. For example, when you take the initial value at 0 and then you propagate over a one-time interval, that's going to give you a different answer than what you got just now by doing a coarse propagation. So there's going to be some discontinuity in the approximate solution at the first time point. And then you correct this by using this recurrence formula here, okay? So what you now do is you propagate, so you look at this recurrence, and then now there are two things on the left and on the right that are indexed k plus 1. Okay, so you have to, but then the subscript, the one that indicates the time points, is going from I minus 1 to I. So you solve this sequentially again, but using the coarse propagator, which again is supposed to be cheap. So that one's supposed to finish quickly. Okay, and then so now that's one parareal iteration. And then for the next iteration, you just do the same thing. So now you have new values for uik, and then now you can do the fine integration again, all in parallel. That's, again, the expensive bits, but you can do this over a shorter interval and in parallel. And then you update sequentially again by the coarse propagator, et cetera, et cetera. Okay? Well, so this is the original parareal algorithm from Lyons and Madé and Turinici from 2001. Okay, so there are many convergence results that's already known. Okay, this list is not meant to be exhaustive. So I just picked a few work that and I listed those, and a lot of these people are in the audience. So if you want to know more about the analysis that has been done, you can talk to people here. Okay, so basically, so the main things that I'm going to say is so the convergence is well known. So for example, if the coarse method is of order p, then after k iterations, you get this estimate where the order p appears here. You also have the superlinear estimate, which was derived by Martin and Stéphane van der Walle in 2007. Okay, so you get this superlinear convergence here. And then you can interpret parareal as a multi-grid reduction in time method. So that leads to a lot of very good and sharp analysis. At least I know that for 2 levels, just like the way I presented here, there's a lot of analysis by Ben Southworth, Stephanie Friedhoff, Rob Falgu, and they're all here. And then it's been analyzed for ODs, and then for some discretized PDEs, there's also an analysis. Martin and Thibault Lunet did one for advection, the advection equation, et cetera, et cetera. Okay, so for 2 level, there's a lot of analysis. For 3 and more levels, there's less results. There's some from the MGRIT community that uses some assumptions about the transfer between the levels in order to get some analyses. And Hessenthaler and co-authors had one paper on that in 2020. There are more, and again, the 3 dots here. I mean, I apologize if I haven't listed, the work that you've done, but okay. In the interest of time, I just list a few here. Now, of course, the issue here, if you have a 2-level method, is that now if you have many coarse intervals, that piece is still sequential. Okay, so if you have many of them, so that could become the bottleneck. So that motivates, whether you can parallelize that sequential piece, okay, in order to get more parallelism out of it. Okay. So of course, there are many ways, there are many variants of writing down, a multi-level parareal method. So this is the part where Martin and I, when we met in Copper Mountain in March 2019, we said, what does this look like? So basically, I just wrote down a parareal algorithm, like the most naive one that I could think of, just to have something that we can stare at. So that was from March 2019, and essentially it's a straightforward generalization of what parareal would be if I added another level. Okay, so now you see that there are, instead of 2 levels, there are now 3 levels. The F and G is the same as from before, and then the H here is basically I slap on an even coarser level on top of the G. Okay, so I have even fewer time points, and now I call this H. And then this goes through like multiple of these subintervals, okay? So now, of course, the H goes farther away. They don't go along the same intervals as F and G, okay? So you can maybe group like M of these coarse intervals into one very large interval. And then so basically, if you want to think about equivalent integration, you know, you have f and g, and then in order to compare f and g with h, you have to compare h with g to the power m, for example. You have to compose m times the g in order to get to the same point, okay? So you're going to see a lot of g to the m at some points, you know, in the analysis. That's normal because you have to go over the same interval in order to compare them, okay? And then I have to introduce a bit of notation here. So I have L of these very long time intervals, and then each of them is subdivided into m subintervals. Okay, so the capital T's are basically these largest ones, and then each of them is subdivided into Ti0, Ti1 up to Tim that's within one of these intervals. Okay? And then the finest scale I don't index. I just think of it, it can be as fine as you want. Sometimes in parareal you even think of it as the continuous solution. Here I just think of it as a very fine discretization, which I consider as my exact solution. Okay? All right, so now here it's a bit of a mess. So the u's are now double indexed because, you know, I have to think about these intermediate intervals. And then at the same coarse time point, I have the y's, which is the coarsest approximation. Okay? The solution, the approximate solution at the coarsest time points. Okay? And then, you know, the end of one coarse interval is the beginning of the other one. That's why there are two of these u's that are lined up at the same, meant to be an approximation at the same time point. Okay? Now I have three propagators, f and g, which go over one of these intermediate intervals, and h that goes over a very coarse interval. Okay? So how does the algorithm work? Again, this is not the only three-level parareal that one can write down, but this is the one that I wrote down just to have something to understand. Okay? So first you go over the coarsest intervals. You just propagate, and then now the coarsest intervals all have initial values that you can use. Okay? Now you have the initial values for the coarse intervals. Now you take one coarse interval. Now you have to propagate that initial value over to the intermediate interval. So there's a second initialization to go from the y's to the u's. So this is still initialization. Now everybody's initialized. So now you run parareal. So within each intermediate intervals, you run parareal. But instead of going over to the whole time horizon, you just basically cut off when the intermediate interval ends. Okay? So you run a small parareal, and then you just basically finish when you don't go across the coarse interval boundaries. Okay? And then, you know, once you run through m of them, you stop, basically. Okay? And then that gives you an approximation that comes after one iteration of this parareal between the fine and the intermediate. And then you use that answer and you inject it onto the second level, which is between the intermediate and the coarse. Okay, so in the intermediate and the coarse, you also run a parareal, but instead of solving the fine, you know, the fine integration exactly, you just take the underlying parareal, you run it one iteration, and then you just inject whatever you get. Okay, so that's how the algorithm works, the one I wrote down. Okay, so you just slap on parareal, and then you just don't solve this one exactly. You just use the previous level. Okay, that's the algorithm I wrote down. Of course, one would suspect that this looks something like MGRIT. So this is the second piece where when I met Stephanie Friedhoff in Valencia in August, I said, there must be some equivalence. So we sat down, so Stephanie translated this into multi-grid notation, and then we looked at what this looks like. And then it turns out that if you do a three-level MGRIT V cycle with F relaxation, then you get this. Okay, this is not exactly the equivalent to the one I wrote down. In order to get the one that I wrote down, you have to erase this line here. Okay, so I do even one fewer relaxation. On the way down, I don't do anything, and then on the way up, I do the relaxation, essentially. So if you even cross out this line, then you get the one that I just wrote down naively. Okay, so there's definitely a relation. So you can use all the gear from analysis of MGRIT in order to analyze what I just did. But I prefer to, well, so here I'm going to present a different analysis that is more closer to the parareal style of analyzing using generating functions, etc. Okay, so of course you could also use the MGRIT theory to do this. Okay, so what am I going to derive? What sort of estimates am I going to show you in the next little bit? So I'm going to show you one where you can actually make it work even for nonlinear ODEs, okay? And that one depends on Lipschitz constants. That's very much in the style of Gander and Heirer in their paper. Is it one of the PinT papers, or is it a DD paper? I forgot. It's a DD paper, that's right, yeah. Okay, thanks. So I'll show you how that works. So there's an analogous way of doing this. And then you're going to see that there's an issue, that there's a place where you lose assigned information and you lose some of the sharpness there. So then then I also show you a linear analysis where you don't lose the sign because you essentially diagonalize everything and everything is a scalar. Okay, so you can just write that down. And then you get a much sharper estimate for the linear case, okay? And then you see that you get a much sharper estimate, but the formula is very complicated. There are sums, there's still generating functions. You can't really write it down in a compact closed form formula. So if you're trying to understand the behavior analytically for many different scalar problems, then you'll have some trouble. So then the last thing I'm gonna do is I'll simplify that estimate in order to try to gain more insight, okay? Okay, so how does the analysis go? So essentially, I look at the errors. So here, I write it as if it was a continuous solution, but in the back of my mind, it's just a discrete but very fine solution, okay? I just abused the notation a little bit. So I have the error between these intermediate time point approximation and the exact solution. I call them E. That's why they're double indexed. And then there's D, which is on the coarse time points. I also subtract that from the exact solution from it in order to get that error, okay? And essentially, I'm trying to estimate these E's and these D's, okay? And the way you go about it, like in two-level parareal, is you assume some Lipschitz constant. So the Lipschitz constant of the difference between the fine and the coarse propagator, a Lipschitz constant of the fine and the coarse propagator themselves, which essentially depends on the properties of the ODE, okay? And then you basically take the recurrence, you subtract the exact solution, and then you do some manipulation, and then you get something like this. So for two-level parareal, this style of analysis will essentially just solve this recurrence, and then that gives you some estimate, okay? So for three-level, you can try to do that also for the coarsest level, between the coarse and the intermediate level. And then what you're going to see is that because I don't use the exact integration and as the fine solve for those two levels, I get a new term here, which I don't know. So this is a term that would have canceled for two-level parareal. So this is a new object that I needed to work with, and that has a recurrence. So you can write that down, and then you can do the same thing. And then what you realize is that now I have a subtraction of two of these truncation error things. So there's a minus here. And if I just take norms, that's going to become a plus. So I'm losing sharpness here. And if it's just a general nonlinear equation that I analyze using Lipschitz constant, that's all I'm going to get. There's nothing I can do, okay? So it turns out that sometimes you can lose a lot by going from a minus to a plus. So then in order to get something sharper, I make the assumption that, okay, now I have a linear problem. I have a spatial operator, which maybe I can I hope I can diagonalize. And then if I diagonalize, then I get a collection of scalar problems for each eigenvalue. And then I just look at the scalar problem and see what that gives me. Okay? And in the scalar problem, I don't have to take norms until the very end, and then I just keep all the sign information. Okay? So basically, I look at the scalar problem, and then I just kept that minus in the recurrence. Okay? And so, in concrete terms, if I just look at backward Euler, then you can write everything as a scalar in terms of the lambdas that comes from the Dahlquist problem. Okay, so f, g, and h are now scalars. Okay, so you have a bunch of recurrences. So what do you do? So the trick is to write down these generating functions. So instead of having I, j, and k, you multiply each of them by powers of eta, zeta, eta, psi, and z. And then you write that down, and that gives you, some function that you can manipulate. There's a lot of algebra. Oh, really a lot of algebra. Pages and pages of it. And see, this formula isn't finished. I put 3 dots. Then on the next slide, I'll show you the full formula. Thanks, 5 minutes. Okay. But you already see the objects that are relevant here. So there's the coarse propagation that plays a role. There's the difference between the coarse and the intermediate propagation that plays a role. And then now there's this f minus g, the difference between the fine and the intermediate that plays a role. There's a finite termination property that you can get just from playing with this ugly generating function. That the point is, once you go back to the indices in L, and then you look at the polynomial, the generating function for a fixed L, it's a polynomial. So when you write down the generating function for a polynomial, eventually the coefficients are going to be 0, which means eventually the errors are going to be 0 once you iterate for long enough. And then it turns out that the threshold here is ml plus L. And if you compare that with 2-level parareal, that's just m. Okay. But now you can also see that if f is equal to g, then a whole bunch of things cancel. So this theorem actually also contains 2-level parareal if you just set the first 2 levels as being the same. Okay? That's not what buys you parallelism, obviously. You want convergence much faster, just as Andy said earlier this morning. So, so you can do this. You can calculate all the polynomials. You can run it in MATLAB, and that gives you some estimates. I'm going to show you how it works out. But it's very nasty. You can't understand anything out of this. So if you want a simpler bound, then what you can do is you can write this, you can use the relationship between generating functions and Toeplitz matrices. And then you can do everything in terms of matrices and matrix norms. You can group them into blocks. Now, of course, you have to be careful not to just apply, say, the infinity norm, because then you'll get the same estimate for like the first n+1 iterations and then the next n+1 iterations. That wouldn't be good. So you want to scale that. You want to do a diagonally scaled infinity norm. I mean, there's a lot of details in here. But the punchline here is you can get something that is of this form, that is a much more compact estimate that shows you that there is some superlinear convergence here. And here the iteration you have to look at, how many n+1 iterations you have done, and then there's a remainder. And then it all sort of goes in here. And then there are coefficients that you can calculate. This one is a lot simpler. I'll show you a couple of examples. This here is just to show you that when you compare 2 and 3 levels, you have to be a bit careful because the cost isn't the same. So I'm going to show you comparisons where the costs are normalized. So let's just take this Dahlquist equation here at minus 0.1. So there are many curves here. The solid ones are the actual errors when you run it for the equation with an initial value and then you subtract the exact solution. The dotted lines are the estimates. Okay? So the blue one is 2-level parareal in terms of the number of iterations. The black one is the 3-level parareal. You see it takes more iterations, but because each 3-level iteration is cheaper, you can't compare them directly. You compare it with a cost-adjusted thing, which is this second blue curve here. And then I have 2 dotted lines, one red and one pink, and they're pretty close for this one, but one of them is the linear bound, and the other one is the nonlinear bound. You see the nonlinear bound, you lose a little bit. Here, it's not so serious. And then the simplified bound, because I also dropped some terms, that this one is a little bit worse. Okay, and that's for so now I'm comparing 40 and 10 coarse and fine intervals for the 2 level, and then for the 40 I split it in 10 and 4 in order to get the 3 level, and then I increase the middle one. And whereas 10 times 32 is 320, so for the 2 level I just put everything in the coarse level. So you see that the 2 level, each iteration costs more and more. Okay, so that's why you have this curve here, and then now you have essentially this convergence for the 3 level. Okay, so at some point the 3 level is going to be cheaper because you have more parallelism. Okay, so now if I change the coefficient for Dahlquist, so you see now you lose a lot if you use the nonlinear bound. So the changing the minus to the plus really hurts you quite a bit here. Okay, and then you see that for the simplified bound, initially it's very bad, but if you add more and more intermediate intervals, it starts sticking better and better to the actual curve that is the black one here. Okay, so that's the scalar case. The PDE case, okay, the heat equation, it just works. Okay, it's supposed to work, so I'm not going to insist too much on it because I'm basically out of time. I'm going to show you an interesting one, which is the advection diffusion equation with periodic boundary conditions that Martin Gander tried in one of the Oberwolfach reports. And this is the one where, if your diffusion coefficient is small enough, then essentially 2-level parareal gives you no speed up at all. You essentially only converge after you've run through your n intervals, and then the error drops. So this is essentially no improvement. Now, because I'm comparing 2 and 3-level parareal, which have a different cost, I basically normalize everything to sequential, okay, in order to show the comparison. So I basically now use 8 coarse intervals because it's the same number of coarse intervals as Martin's example. But now I refine the 2nd level grid to go from 2 intervals to 64 intervals. And this is the cost normalized one. If it's above 1, it means that it's cheaper to run the sequential. And if it's under, then you get some parallel speed up. Okay? So you see that 2-level and 3-level, if you don't put enough intermediate intervals, then essentially they're both worse than sequential. And then you see that as you add the number of add coarse intervals, the 2-level one essentially just stays above 1, so no improvement. But the 3-level, you start getting something interesting, right? So now the cost is below 1. I mean, you're throwing a lot of processors at it, but at least you get something out of it, which is not the case if you only have 2 levels. Okay, so this is something that I observed. Ideally, if I had more time, I would use one of these simplified estimates that I showed you earlier for different eigenvalues in order to see whether I can reproduce this behavior here. Okay, but now I'm out of time, so I'm just going to stop here. Thank you.
Yes?
So I was curious if your analysis at the end of the day, if you could look at it and if it can kind of tell you anything about how the coarse and fine need to relate to get good convergence.
That's
not clear to me looking at it. That's why I'm curious if you thought about this.
I have thought about it. Basically, we're at the point where if I can compute the difference in the propagators between coarse and intermediate and fine, I can compute everything. Now, the design will probably also depend on how each propagator varies with the lambda, because you're solving it for many lambda. So that part I haven't looked at yet.
There was another question, I think, Olga.
That
Oh, these examples, I use backward Euler for everything, but there are also other examples that I didn't show that uses a higher order integrator for the fine. The very last one.
It's advection, diffusion, equation.
Oh, that's backward Euler everywhere.
Backward Euler, but I guess this is okay. And so your numbers there are telling us what's the discretization of each one of the.
Yes, so I look at the backward Euler, I run the backward Euler, and then I essentially look at how many iterations it takes, and then these are raw iteration counts, and then I normalize for the cost, ignoring communication costs. So I just say one backward Euler step takes a certain amount of time, and then that's my unit, and then I just normalize. Okay, thanks.
Okay, I think we should continue. Let's thank Felix once more.
Okay.